welcome everyone to our first Motion Revision EBM or webinar for Complete VCE. For those of you who don't know who we are a specialist tuition company. We specialize in only providing VCE physics tuition to physics students. We've been doing this for more than 6 years, and we've taught more than 500 students, with the majority of our students achieving above a 50 raw score. Sorry, about a 40 raw score, and have done fabulously well in the exam. So we kind of know a bit of the secrets in terms of how to game the system and do very well. And we wish to share some of the insights with you guys for the first SAC as well, coming up very, very soon. There are some common tricks and traps that schools and examiners will utilize to try to, get some marks off one or two people. So in this webinar today, we'll cover some of the main important points that we should not overlook when we do our first assessment. So technically we're starting at 8:05, but I think a lot of us are here already. So we probably don't want to waste any more time, and we can get started. So why don't you turn to the next slide for us, please, Eric?
Yeah, welcome everyone. So I feel a bit stressed about the SAC upcoming next week, tomorrow, or about next month, or you're just here for extra information. This is where you go, right? So today's webinar, I think the purpose is to maximize your performance. And we have prepared 8 questions in total, and we try our best to go through it within 1 hour. If we couldn't do it, they'll be sent to you with solutions written by Excel, which we'll introduce later on. And you can get all the answers and responses. And we also plan to record the meeting. So you can watch the recordings if you want to review what we have done today. So the sessions for 3 types of students. The first batch is for those who aim for perfect 50. So want to be the best out of the best. The second batch would be students that are doing very well, but you want to strive for excellence, right? Want to do better, and you're welcome here. And the last one, which is maybe perhaps one of us, when we are just starting to do physics, is we found the subject very challenging. Physics is no easy subject. I've done physics for about actually 12 years already. So I know how difficult it is at the very start, but the secret is you get better with more practice. So today we have me and Ralph to guide you. So we do a bit of introduction before we start. Ralph, take it away.
Quick note on that, Eric. I think back to the previous slide.
Yeah.
Yes, it's really for all types of students. I think in this group here, there's about 50 something of you. We'd have a good spread between all 3 types. Some of you probably a minority, no more than 20-30% aiming for raw 50. You'll find this webinar very helpful because halfway through and towards the end, we have some very hard questions. We call them differentiator questions. So these are questions, right? In every single VCAR final exam, there are about 5 to 10 marks that are very, very hard out of 130 marks, short answer and MCQ, that differentiates the people that score 45 plus to a 50. So stay tuned for those ones. That's going to be very, very interesting for you and pretty good fun as well. And again, for students who are, maybe struggling a little bit and maybe all you want is just to pass your next Motion SAC as well, we've got you covered as well. In the VCE physics exam, it's pretty, equation and mathematically heavy. So by the end of the session, we'll send out some formula sheets, summary sheets as well for you guys to study. And as long as you guys are relatively familiar with how each of these equations works, the use cases for them, and know how to calculate these equations properly, you can do, at least decently well so that you stay afloat for the next few assessments. So it's I've got everything for everybody, so stay tuned. And yeah, we'll do a quick introduction as well about who we are. So I'll start with myself. So my name is Raphael, and I'm the founder of Complete. We've been in business, like we said, for about more than 6 years. And the reason why we only focus on just one subject, physics, is because I believe that's the only way we can deliver a very good service in terms of the materials that we provide, the teaching experience, as well as the statistics in the exam and the tips and tricks on how to ace every single SAC and the final assessment. I've got a day job, so I'm a final year medical student at Melbourne University. And yeah, that's something I do on the side. I love physics very much. And yeah, we'll have some fun today. And we'll move on to Eric next.
Fabulous. Thank you, Raf. And similar to Raf, outside of doing tutoring, so I'm now the general manager of Complete. I'm also teaching VCE Physics in a high school daytime. So I teach STEM and physics. They're my specialties. I taught overseas and local. So about 6+ years of teaching experience. In counting kind of the internship experience, I think I got close to 7 or 8 years. So I know physics for a very long time. I came across 3 different curricula, and I got my master's of teaching in Monash. So um, excited, love to share the knowledge, and hopefully we can deliver a very good session for each and every one of you here. And Asel, who's not here today, he's actually with you guys because in the PowerPoint slides, you're going to see everything about him when he is doing the Raw 50 thinking. So he's the head of our resources. As you can tell, he is academically very driven student. He joined us, I think, 2 years ago to start to manage our resources. So 99.95 ATAR, 50 Raw in physics, and he is the person that drafts the answer for all the questions we're covering today. So we can learn directly from the best of the best.
And the next
Okay.
slide, just have a brief summary of the resources that we'll provide. So again, just to reiterate, a handout with all the questions and solutions we'll cover today. We'll be focusing on quality. So we'll be going through some of the harder stuff that I think is important. We'll take time and go in depth and explain them properly. So don't feel pressured to stay for the whole thing. If you don't want to, we'll send you handouts so that, for the questions that we haven't done, you have some practice resources. We'll also send you guys, for all attendees that's come in with us, a mock SAC with solutions, a formula sheet and summary sheet for the first SAC. And for new students, you're welcome to book in a free 15-minute consultation with us. If you're still looking for a good physics tutor and you want to plan out a strategy for how to do a bit better, do book that in. We'll post the link for that in the chat, just in the Zoom here, as well as subscribing to our free resources on our website. You can submit your email and you'll get all our notifications. So without further ado, guys, let's get right into it and get kickstart with our first question. And just before that, we'll quickly touch on the webinar structure. So the first part, we'd be covering some MCQs. So there'd be 4 MCQs. And the second part, we'd be doing SAQs. And with every question, we'll kind of break it down by, 2 categories. We'll kind of tell you guys kind of what the examiners are looking for when they constructed the question, what they're really, looking to test out of you. And then from the other perspective, as a top student, how you can approach these questions to do very well. Okay, so without further ado, guys, let's get started with our very first question. Every question will give you guys about a minute, plus or minus, given, depending on the difficulty, for you guys to try. So guys, have a notebook or something with you, an iPad, to take notes and try these questions yourself as we go. We want this to be as interactive as possible to emulate our normal teaching experience in our own classes. So yeah, we'll get started. So question 1, let's take a read. A skydiver is falling and has reached terminal velocity. So we'll do a quick diagram here. So let's say that's a skydiver and it's reached terminal velocity. So let's call that VT, terminal velocity, which actually means the fastest velocity you can go when you're falling, free falling. Which of the following correctly identifies the reaction force to the gravitational force exerted by the Earth on the skydiver? So probably give you guys a bit less than a minute for this one. And yeah, have a try and we'll go through it in about a minute. Cool. So just finalizing your answer, guys. And time's up. Good. I think quite a few of you got the answer ready and maybe private messaged me or the group. Cool. So if you guys chose A, that is the correct answer. So A is the correct response here. If you chose air resistance, I think that's the next common answer. That is in fact wrong. So that's a very kind of intuitive answer, but that's in fact not the correct answer. So Eric, if you don't mind pulling up the working on the side, we'll take a look. So, what are the teacher's insights here? So, what they're really testing you guys is an understanding of Newton's third law, which is that every action has an equal and opposite reaction, and also understanding that terminal velocity is defined when F net equals zero. It's defined this way because terminal velocity, by definition, is your fastest velocity. If you have a net force that's not zero, it means that you have a non-zero acceleration. You can't be traveling your fastest if you have a non-zero acceleration, right? If you think about it, if you've got a negative acceleration, it means that you're slowing down. That means that you were traveling faster before. If you have a positive acceleration, it means that you're traveling faster and faster. It means that you haven't reached your terminal velocity yet. So the definition of terminal velocity is when F net equals zero. Eric, let's get the next part on. Cool. And you can see a diagram here, which is there are two forces acting on your object. The first one is gravity acting downwards as usual. And the second one is the resistance or the air friction acting upwards. So if F net equals zero, by definition, these two forces must equate. So we equate these two forces, Fs equals Fg. And for a lot of questions, that's how we start and that's how we do the question. For here, a very common, again, a very common answer students give us is, okay, the reaction force is just the resistance force pushing upwards because they kind of cancel each other out, right? But again, that's not correct. From Newton's third law, right? An equal and opposite reaction must act between two objects. So very simply speaking, if A pushes on B, B must push back on A. So we'll do a quick diagram so that we're illustrating what we mean. If you've got two objects, objects A and B, imagine A is the instigator, right? So A pushes on B, and we call this F of A on B. If A is pushing on B, Newton's third law by definition has to be from B pushing back on A, right? So it'd be B on A, okay, F of B on A, and we call this an equal and opposite reaction force, and that satisfies Newton's third law. But it has to be acting on two different objects. It's two different objects acting on each other. In this case, you have two different forces acting on the same object. Gravity acts on the object, and air resistance acts on the same object as well. So by that definition, it can't be Newton's equal and opposite reaction force. If you zoom out, right, instead of going all the way in, zooming into the skydiver, you look into the bigger picture of how things work. You have the Earth here, okay? And you've got a skydiver that's kind of falling down. And the Earth exerts a force on the skydiver, and we'll use a different color to highlight that. And that's the gravitational force, right? Let's call that Fg, the gravitational force of the Earth acting on the skydiver, pulling it down. And therefore, the equal and opposite reaction force should be the opposite, where the skydiver, its gravity acts on the Earth as well to pull the Earth up. Remember, gravity acts both ways. Two objects pull each other together. And so if the Earth is pulling the skydiver down, the skydiver is also pulling the Earth down. Now, the obvious question some of you might be asking is, that doesn't make any sense at all because the skydiver is the one that's falling down. The Earth is not budging. You're correct. That's very much the case. And it's also very true that the gravitational force that we have here, they're both equal in magnitude. But the reason why the skydiver is the one that's moving all comes back down to Newton's second law, which is F equals ma, okay? Even though the same force, the same gravitational force is applied on both the skydiver and the Earth, because the Earth's mass is a lot larger, okay, it doesn't budge as much, right? The acceleration of the Earth doesn't move as much. So despite how non-intuitive this may seem, the answer is actually A and not B, okay? So A is the correct answer here, guys. Take a note. And open to any questions as well, either in the chat or you can just shout it out if you'd like, but otherwise we'll move on.
So I just want to point out, Raphael, I was monitoring the chat. So it seems like many of our students, are got the right answer. They got A. So I feel like we can try something more challenging. Is this something that we can do?
Definitely. So we might skip question 2 then, and we might go through question 3, which is a bit more challenging given our limited time. Okay, got a question. Do action reaction pairs act on the same or different objects? They act on different objects. Okay, so if A acts on B, the reaction, the opposite reaction force has to be B on A. Okay, so very simple. If A acts on B, B must act on A. In this case, it's between the skydiver and the Earth. The Earth is pulling skydiver down. Skydiver pulls the Earth back up. That's an action reaction force. Great question there, Ariman, and we'll move on to the next question, Eric. Okay, so now this is a very challenging question. So maybe instead of 1 minute, we'll give you guys a bit more time. We'll give you maybe 2 minutes to try this one. So a block of mass M is attached to a vertical spring with the force constant K. The block stretches the spring and comes to equilibrium, storing an elastic potential energy of E. Now, if the mass is reduced to 0.5 mass, which is half the mass, and the spring constant is doubled to 2K, what is the new elastic potential energy in terms of E? So these are one of the differentiators you'd get in your SACs or the final exam. I'll give you guys 2 minutes and I'll start the timer now, and good luck. And again, if you guys get the answer early, do DM me or just shout it out. Probably DM us actually, so we get a gauge of completion as well as the range of answers we're getting. Okay, about 20 more seconds to go. If you've got an answer, do let us know. Quite a few of you guys chose C. Unfortunately, that's incorrect. Okay, so a few more seconds and we'll go through it together, guys.
So Ralph, I got answers A, B, and C as well in my private message.
Okay, well, this is a hard question for a reason, right? It's a differentiator question for a reason. It differentiates, and we've got a good range of answers. I think a lot of you guys put A, B, and C, some Ds. Now, what is the answer? So I'll circle it now. If you guys chose D, E on 8, that's the correct answer. So very good job to those who chose D. Now, let's go through why that's the case. Now, you have a spring, okay? And you have it initially at an unstretched position. So that's its resting or unstretched position, okay? And then it gets stretched, okay? We lower it so that now it's at equilibrium. So we come down to equilibrium, okay? And we want to find a new elastic potential energy. Now, quick note, guys. If we have an equilibrium question and it's settled, we always use forces to solve it, right? So equilibrium in springs, right? So in the broader topic of springs in motion, if you have an equilibrium question, that is settled, okay? A settled equilibrium question. So let me write that down. Settled. We always use forces to solve it. So what does settled mean? Settled means it's not moving. Okay, so this block now is in the equilibrium position and it's settled, which means it's not moving. We always use forces to solve it because the forces balance out. Okay, if we have a non-settled question we call it an oscillating or an unsettled question, we use energy most of the time, right? So like it's 99% of the time. Sometimes there are exceptions, but if it's an oscillating question, for example, it's not one where it's already in this question, like it says, it's already in equilibrium position and it's not moving. Whereas, for example, you release it from the unstretched position and then it starts to accelerate downwards and then it goes up again and it oscillates up and down. In these questions, these are unsettled. We use energy transformations to solve them because in an unsettled question at the equilibrium position, well, you're not settled, right? So you don't have a neutrality in force, and therefore you have to use energy. So that's a quick note. Now, Eric, if you don't mind pulling up some of the working on the side, we'll go ahead and try to solve it. So what are the insights from this question? We want to know the Hooke's law, F equals kx, and utilize that very well. We also want to know that you guys can use the formula E, or elastic potential energy, ES equals half k dot x squared, some algebraic skills as well, okay? In terms of how to actually do it, Eric, do we have kind of like a diagram for this one to... Perfect. Okay. We look at the situation before and after, right? So on the left side here, we have before, which is just with a normal mass and a normal spring constant. And on the right, we have after, where the mass is halved, okay? And then the K, or the spring constant, is doubled. Okay. How do we solve this? Well, I'll give you guys the broad structure first. The formula for elastic potential energy, like we mentioned before, is ES equals half K dot x squared. So some of you might try to solve it, right, by hand. We're like, okay, half K dot x squared. We have got the half there, that's fine. And then for K, how about we sub in 2K? Because we know that the spring constant has doubled, right? So 2K, and then we can sub in delta x as well to find what the new elastic potential energy is like, right? So that's one idea that we may have. And you quickly realize that we can't really do that because even though we have the new K is doubled to 2K, we don't really know what the new extension of the spring is, right? What is the new extension of the spring when the mass has been halved and the spring constant has been doubled? We don't know, right? So we need to find that. And the way to solve that is through a series of algebraic expressions. So Eric will pull it up. Now look at the original situation, right? So we'll pull it up slowly, Eric. So very good. So we've got two forces that are at play, right? We've got gravity, as always, pulling down, okay? Fg pulls down. And then we've got Fs. Fs is our spring constant that pulls, also the spring force that pulls up. In this case, we know that Fs equals Fg. Again, because this is a settled question, right? That's a settled equilibrium position. Because it's settled, it's got no acceleration because it's not moving. So it doesn't accelerate. Since F equals ma, when you have no acceleration, you have no net force. So because there's no net force, we know that Fs balances out Fg. And then now we can plug our expressions into our working. We know that, Fg equals kx, mg equals kx. We can solve some algebra and get an expression of delta x in terms of mg on k. And then now we can plug the x, right, or the extension into our kinetic energy, our spring energy equation to find the new spring energy. So I think the working out for the second part is a bit confusing, Eric, so I might just actually annotate myself if that's all right. So let's do it for the new situation, okay? So we've still got the same system. We've got Fg pulling down and we've got Fs going up. So then we say Fs equals Fg. So hopefully everyone's following so far. I think it's relatively straightforward here. Now we can sub in mg is equal to kx. However, there is a change here, right? Our mass has been reduced by half, and then our spring constant k has been doubled to 2k. We got to factor that into account. So we put both of those in. We say that half mg is equal to 2kx. And now we can find an expression for x, or delta x, they're the same thing, to be equal to, what is that? So mg on 4k, okay? Or 1/4 mg on K. So now we're almost there. We use this new delta X. We plug it into our new equation, okay? And we get ES is equal to half times 2K multiplied by delta X squared, which is 1/4 mg K squared. And so everything cancels out, and you end up with 1/4 squared, which is 1/16, multiplied by your new 2K. And so 1/16 multiplied by 2, you get 1/8. And so from that, we know that D, or E/8, is our final answer. Okay, so a bit confusing, guys. I'm sure that at the moment, some of you guys still need to work the numbers through, but look, you're not meant to understand this right away. It takes time. So once we finish this webinar, go back, look at our solution working, and you should be able to calculate for yourself that E equals, 1/8 of the original. So do take a time afterwards to work the numbers out again so that it makes sense. Okay, so that's all from my part today. Again, we skipped question 2 and question 4. It's going to be in our solution template. We're going to send that to you guys after the webinar. Now I'll hand over to Eric.
Thank you, Raphael. Just before I move on, I encourage you guys to ask any questions. And if you want to take a screenshot, that's perfectly fine. I just want to point out Excel actually has an alternative method. So if you join the webinar, you can also receive the handout. You get to see 2 ways to do the same question. So that'll be fabulous. All right, that's the case. I'm going to move on to part 2, which is about the high yield structural questions. And in fact, it contributes to 100 marks out of 120 in VCE. So you don't want to miss this out. All right. Same as usual, we're going to start from something, rather straightforward. But as I say straightforward, it is created by me. And as a teacher, I like to set up, some concept traps to see if my students really understand everything. So let's begin. Raphael, I think we need a timer for about, let's say, 1.5 or 2 minutes. Okay, so everyone give it a try to read the question to see the 2 views of the situation. There's a marble going in circles inside a cone. The length between the marble towards the bottom of the cone is given. And we also have the angle of the cone that's banked 60 degrees to the horizontal. And your task is to find out the velocity of the marble, or should I say the magnitude of velocity? So you just want to find the speed. Assuming there's no friction between the surface and the marble itself. So I think the clock is ticking, and feel free to send me your answers. So there's about 20 seconds left. I know it's very rushy, and I just want to make sure everyone got enough time to try. I start to receive some responses. So we'll wait for another bit. Perhaps another 30 seconds after the timer takes to 0. Okay, I'll wait for another bit before I start explaining. Okay, feel free to type your answers or send it to me or Raphael through private chat. I got several. Appreciate that. And it's very interesting. Well, all 3 answers are different. So it's a very good question to do. And you should be very glad that you attend the session, because if this pops up in your SAC, you really want to know how to do this. Okay, so I got a variety of answers, which means I set a very good question, Raphael, I think, to differentiate between the students. So look, let's look into it. Okay, I think the first thing I want to share is from my perspective, right? From a teacher's perspective, what I'm thinking. The first thing I want to point out is that the length provided to you, it's not necessarily the radius. Okay, so for circular motion, there are 2 ways they could do it. you should pay really close attention. So one thing they would do is to provide you with some random length. So in this here, this is not the radius of the circular motion because it's rotating about this plane, right? This plane over here. The radius should be this one that goes straight from the ball to the center. Okay, so what's given, it's not the radius. Sometimes they would draw a circle and they would give it diameter, right? That's another way to confuse the students. So please pay close attention. The other thing is the forces and vectors addition. This is a very important skill for me to test out. And for some of you, you may even use methods like resolving components. That's another thing, okay? So a cell, provided us with a solution, what is in its mind? Okay, so first things first, this relationship is always true for circular motion, okay? So we usually wrote down net force as ma. For circular motion, not only that part is true, right? And A stands for centripetal acceleration. All right, so F is equal to ma. That's true. However, for circular motion, what makes the ball go around, right? There must be a force that always points towards the center, okay? And that has to be the sum of all forces in this diagram. So speaking of diagram, you must draw a force diagram. So unlike this one and that one here, there's a third diagram you should draw. And later on, you may also consider to use this equation to solve any problems, okay? And so I'll walk you through about how to approach these questions. First of all, find the actual radius, okay? So that involves a bit of use of trigonometry. So you can see from the image right here that I labeled 60 degrees because these two angles are the same, and I extended to make a right angle triangle. So that'll be R equals to the length, which is 20 centimeters times cos theta. So some of you type in the messages says that, yeah, it says centimeters. So there's a trick. Whenever you see something that's kind of weird in the question, right, you just convert it straight away, right? So sometimes if your brain's lagging, I can put 20 divided by 100 and I'll let the calculator do the work. Some say 0.2 straight away. That's fantastic. The mass as well, you can convert to kilograms. Right, divide this by 1,000. So if you spot anything unusual, just do the conversion here, or at least just write down the fraction or the expression for the conversion. So nonetheless, you should get the radius as 0.1 because if this is the angle, that's theta, that is the hypotenuse, and that's the adjacent, right? So SOHCAHTOA, you use cosine for adjacent over hypotenuse, and that's the way to do it. Okay, so that's the first important step. Show thumbs if you get at least the radius correct, because that's necessary for the next two steps. I'll wait for a bit. So if you get this correct, or after explaining, you totally understand what's going on. I want to see some reaction. Show thumbs. Yep, I see the thumbs up popping off. Brilliant, brilliant. And I think when you get the radius done, all you need to do is to practice on how to draw the forces. Fabulous. I'll clear all drawings and let's move on to the next page, which is here. Okay, so Assel's next step, right? What he's going to do, he used a vector triangle to find centripetal force. Well, this is something I diverge with him because I like to resolve forces, but his method is very simple and neat. And I'll show you how to do it. The first step is to draw the vector triangle. Okay, so you draw a triangle and use trigonometry. So there are two forces acting on it, right? The first one must have is the gravitational force. So you can put it as Fg or mg for simplicity. And the other force is the normal force, Fn. Now, some of you may question, hey, Eric, shouldn't we draw the force, especially the normal force is from the point of contact, right? Yes, we should. That's exactly the way to do it. In here, it's just for presentation. I decide to draw all forces from the center of mass because I'm going to show you something cool next is how do I make a triangle out of this, right? Because there are two forces acting on it. When you add them together, it forms a net force. So how do I draw the net force? Okay, so one thing I avoid to do is to draw the third force. That may confuse yourself. In fact, in your brain, you can try to imagine something like this, or you draw on the side. And I'll show this now. So you shift the gravitational force, right? Using head to tail method. So you join the arrows together and you draw the net force. And you can see this force, it's perfectly pointing towards the center, right? And just like what I said, right? For centripetal motion, like for circular motion, the net force must be a force that's always constant in size, and it always point towards the center, right? So F net is FC. And you can also get a 60 degrees between MG and FN. So that forms another triangle, okay? So here you go. That is the expression, okay? So 60 degrees, and you use the tangent simply because what's given is the adjacent, right? For MG is the adjacent, and then, it should be the opposite. Opposite for F net equals to FC, so O and A, so that's opposite over adjacent. I'll try my best to do handwriting for mouse, but here you go. And then the next step is to substitute the values in, right? MG tangent 60. Now I see a question that's very important. So it's not off topic at all. We should use 9.81 as the value of G because VCAT just released the latest formula sheet. Every constant on that piece of paper is written as 3 sig figs. Okay, so no more 9.8. If a teacher's doing that, I don't think they're doing the right thing. Please make sure you use the 9.81, which is the latest information we got from VCAT. And so there's also a question about derived formulas, and well, I'll go through that very shortly. So thank you for the questions. So anyways, you should get the centripetal force as 0.510 newtons based on this method, okay? So does that make sense to all? Again, you may notice I kind of slow down a bit because there's a multi-step calculation. I'll make sure everyone's on is on with us. So does that make sense? If it does, please show thumbs. And I think Raphael and I can see in the Zoom. Fabulous. Yeah. And Raph, you're going to help me out. We got 3 pages of participants. I can't check every one of them. So if you can just go through this very shortly and see if we got many thumbs ups, that'd be great.
I think most of us understand pretty well. We can move on, Eric.
Fabulous. So I'll move on to the next part. And actually the last step, right? So the last step is to summarize everything, right? Once we got the radius, once we got the centripetal force, we can rearrange the formula to say V is 1.3 meters per second, okay? Meters per second. So look, once again, for multi-step calculations, a lot of people tend to use different ways. And I myself, I may do something like I solve by components. I split, I split the Fn into two arrows and I solve it with components. And later on, I derive the formula that tangent theta is actually V squared over GR, right? You can certainly do that. Now, if you can use, let's say, can you use a question like this in the exam? Okay, it really depends on how many marks are there for the exam? Okay, so let's say it's a 2-mark question, right? It's a 2 marks question. Then 1 mark must be for the steps and 1 mark must be for the answer. Okay, and for steps, I mean for correct substitution. Okay, so if you demonstrate correct substitution, you get the mark. You get the correct answer, you get the mark. Simple as that. Now, it's pretty risky if it's like a 4-mark question and you don't derive the formula from scratch because chances are some of the marks are allocated for you to demonstrate your understanding as to how the formula is derived or how does that come up, okay? So I would suggest, yeah, to derive the formula, right? Just like what Estelle did step by step. If it's a multi-mark question, if it's just 2 marks or multiple choice, don't worry about it, okay? Just use the formula that you have. And some say, yeah, it will be easier, perhaps. MV squared over R divided by MG and simplify, it's totally. And I think this is what I did here to get the tangent theta formula. Yeah. And so just want to emphasize again, G is not 9.8, it's 9.81. I think that's something I need to reiterate. It's very important. So please make sure the change and you keep abreast of that. Okay, so anyways, if you're following from start to finish, all right, you should be able to get, or at least to understand how we get 1.3 meters per second, all right? And look, there's some useful tricks you can do with the speed. Everything in VCAR and VCE must make sense. Like the marble cannot go in speed of light. So it's a sensible answer. Every second goes by 1.3 meters. It's actually quite fast. Okay, so here you go. Before I move on to the next one, I just want to stop and pause again to make sure. Yeah, I got a question saying the school teacher tells you to use 9.8 because the study doesn't say so. Unfortunately, you can check, the 2024 in the formula sheets, the constant is all provided as 9.81. Okay. In fact, if Raphael can send through the link, you just type in VCAR formula sheet physics, and you can see that it is changed. And yeah, in the past, I think it's correct. But this is the new policy. All right, so if you found this question pretty challenging, make sure you book in a consult with us so we can better see, what the school's doing. So I appreciate all the comments and feedback that I'm having now. Yeah, just sign up as Raphael posted the study design formula sheet, and later on perhaps the link for the consultation. That'd be fantastic. Yeah. Totally get you. I got a direct message saying that they're not very happy with what we are a bit ambiguous. Right. So this is something we definitely need to keep attention, right? Paying attention to. So I think joining the webinar is the first step you can do to get more information regarding this. Anyways, I'll move on. We can check out the academic consult that posted in the chat. So I think we got some time for another question. Okay, so let's do another question today. I like to do something different. Okay, so something maybe towards the very end. Just so I'm aware of the time, I don't want to take up too much of your night. So make sure that time is spent on something that the most important thing is. That'll be question 4. Okay, so it's a multi-step question. Okay, so it usually happens in the exam. We got 1 or 2 questions like that. That's like a 10-mark question from start to finish, and that involves the use of many formulas. All right. So perhaps I think a good way to start, all right, is we can set a timer. That's about 2 minutes. Now, I don't want you to do all the questions. I don't need to calculate the answers from start to finish, but at least what I want you guys to do is to state which equation you like to use for A, B, C, and D. Okay, so show us your thinking. What sort of method? Is it SUVAT, is it forces, momentum, or energy that you prefer in solving A, B, C, and D? And afterwards, you're going to walk this through. Okay, so that should be more than enough. You should have time to think of this, and we'll check in about 2 minutes. All right, if there are any questions, please make sure you send to us. And don't forget, you can book a free consult at the meantime. It's about 1 minute left. So again, don't stress on finding the answers, because once you get the equation, you should be able to solve it. So here is just the methodology and the thinking. It's what we're trying to focus here. Okay, if you've got any ideas, A, B, C, and D, which method you'd like to start, you can type it in the chat. And actually, I got one. Thank you so much for sharing this to everyone, CJ. Okay, many ideas. I like it. Yeah, I got many direct messages as well, so that's perfect. Energy, momentum, SUVAT, energy. All right. Here comes the music. So in the meantime, let's see actually what's inside my mind when I set this question. Okay, so this question, again, inspired by a VCAR question that looks very similar, but the only thing that's different is I removed the picture. So let's see. Insights. Students are often found to have confusion to see which concepts are relevant to which part. So even though I'm pretty sure, as I explained this, 100% of you, you can do this mathematically. But physics is more than that, right? You have to visualize complex scenarios, and not only that, you're going to choose the right formulas to start from. Okay, so today I hope I can teach you some of that and share some insights on how to do this. And Asel, his thinking would be always draw a diagram for these motion equations, okay, or questions. We always draw diagrams. Okay, so let's say for the very start, it looks something like this. Okay, we got a block, 0.8 meters high, 1.6 kilograms, and there's a 0.4 kilograms block waiting for it to be collided. It's 1.2 meters to the ground, and there's like a 0.1 meters sliding distance. 0.1 is actually coming from the centimeters, right? So something we did earlier is to change this into kilograms, change this into meters, change this into meters, just to make sure everything is in SI. Okay, I think that's the first thing you should do as you read the question. So please make sure you use that during your reading time, right? Read all the questions carefully and draw a diagram because it helps your thinking by so much. Afterwards, it just, follows a projectile motion. They fall together after they stick together after collision. So let's start from the first part, right? The first thing is to calculate the speed of block A before the collision. So many of you suggested like SUVAT, I heard energy as well. It seems like energy is the better way to do it because it's simpler, right? You don't need to consider any sort of direction. Usually for speed calculations, we can use energy as a first try because you can see the masses are taken away, right? So I skipped a step here. I took away the mass on both sides. I rearranged the equation into square root of 2gh, and notice that I use 9.81. And so you get about 4 meters per second. Okay. I would make sure I kept this value somewhere written down on the paper so I can, backtrack this whenever I need to. So that's about 4 meters per second in 2 sec-vecs. So it seems like many of you have got the right answer, right? You start to use the energy equation to do it. For SUVAT, is it even doable? Doesn't seem like it. I don't think you can solve this one with SUVAT, unfortunately, because you need to know what the angle is over here. You only have the height. Yeah, so I don't think that's enough information just by intuition, or even if there is, it'll be so complicated, it's not worth the time to even try SUVAT in the first place. Okay, so it's very important that if you use this as the ground, there is some MGH for block B, right? And there are two, and sorry, so let me restate everything. So if you set this as the ground level, okay, that's the original height. So you're gonna add the total, and it becomes final when block A is here. There is two types of energy, right? There's GPE and there is the kinetic energy. So the whole thing is just more complicated. So I think what Asel would suggest is you delete everything. You set the ground level to here. So it's an easier question to do. Okay. Now, next part is to think about collisions, right? So when you say combined blocks after collision, collision is a very strong hinting word to use a momentum. So we can use the conservation of momentum. It's an equation that everyone knows, right? MAUA plus MBUB is, now this time, I can treat this entire thing as a single mass, as they stick together after colliding. So they move in the same velocity, right? And you can take the total mass of the two blocks, and that's how we do it. So you sub the values in, okay, nothing fancy, to get V equals to 3.2 meters per second. Okay, so this is, you can even state that it's going to the right-hand side, but since we're finding speed, it's not necessary to state the direction. So again, as I said, if you look at the maths, it's rather simple, but I think the hardest thing would be to decide which method to use at the first place. So I'll pause here a bit just to see if everyone's happy with parts A and B before I move on to C and D. Again, show thumbs if you are understanding. right? If you're not right the first try, that's okay. If you understand now, I want you to show some thumbs and, fabulous. Wow, we got a lot of thumbs ups. That's great. So I'll move on to the next bit. Now, part C is a classic question to determine whether it's elastic or not. And usually it's like 3 or 4 marks. The way I'll present it is I'll have 2 blocks, which is to found the initial and final kinetic energies. Because momentum doesn't really help in this case, because elastic or inelastic, in those 2 cases, the total momentum is conserved, right? So before always equals to after. It could be handy, just like the case we did. We're trying to find the final speed, right, after collision. But that's very helpful. But it is not really helpful to distinguish between elastic or inelastic collisions. Okay, so we compare instead the total kinetic energies before and after. So please be very careful. You're going to write the terms for A and B separately. All right. Luckily for B, we have no initial speed. So this whole term is 0. We just evaluate what's in here to get 12.5 joules. Afterwards, you can treat that as a combined mass moving together at the same speed. So same thing here. That's 2 divided by 2 times 3.17 squared. And that gives you about 10 joules. Okay, so 10 joules is the answer. Now, the thing you can realize is it's not conserved, right? Before it's greater and after it's lesser. So some energy is lost in this interaction, which means the collision is inelastic because the total kinetic energy is not conserved. So in the past, I reckon there are 4 marks questions like that, which 1 mark is dedicated for inelastic. The other mark is for justification. Modern VCE would say 3 marks because you can kind of guess elastic or not. So they don't give you marks like that. You're going to have a valid reason to justify why this is inelastic. So that total statement would be worth 1 mark. Okay, let's still see any questions. Yes, and I love the insights you're bringing. In fact, without doing any calculations, I can say for sure this is inelastic because the objects stick together. And in fact, this is called a perfectly. So perfectly, I'm sorry for the handwriting, but trying to use the mouse to write. Perfectly inelastic collision, which means it's the collision that has the most kinetic energy loss, right? The only way to achieve that is to have the objects stick together after the collision. That is called a perfectly inelastic collision. So yeah, if it's a multiple choice, right, you can say definitely inelastic. Why is that? Because they stick together. That's called perfectly inelastic collision. Thank you, Raphael, for adding the words. Appreciate that. Okay. So let's move on to the last part because these are very classic questions. The last bit would be about projectile. So to calculate how far it is from the platform as they land and fall off the edge. So it is important to realize that the blocks are moving horizontally off the platform. Okay, so it's a horizontal projectile motion. It's at 3.17 meters per second, and it's influenced by gravity. So step 1, the only thing that connects between horizontal and vertical, right, is the time. So let's say if the blocks are here, just before, moments before they reach the ground, right? Doesn't matter which perspective you're taking, right? You can see the horizontal displacements, you can take a look at the vertical displacements, okay? They must reach here at the same time. So the first step is to find out the time to fall. And you can use the SUVATs, right? And take downwards being positive, and you sub in all the things above vertical. Okay, now since we're taking downwards being positive, so this 1.2 is positive, right? Displacement is positive. 9.81 gravity, was pointing down. So this gravitational acceleration is also being positive. You may notice that this entire term is gone because of the initial vertical, right? The vertical speed of velocity is 0. Okay, the block was here. They stuck together, and that's the initial velocity, right? So we can move on to the time, 0.495, and afterwards, find the horizontal distance, right? Same equation, right? These two equations are actually the same. You see that the missing part is the acceleration part of it plus ax 1/2 ax t squared. That is because in VCE, there is yet to have any questions with horizontal acceleration. So we simply use s equals to ut to find the answer. And you put in the initial velocity times the time to get 1.6 meters, okay? And that would be the final answer. All right, folks, that's all we have for now.
Right. Okay, so let's call it a night, shall we, Eric?
Yeah, I'll stop the recording now.